Hey guys, today we are going to learn about Morris and order traversal by threading of binary tree. So this is an actually a very it's a very interesting algorithm, and it is basically used to do the traversal of a binary tree. It can be pre-order or it can be in-order traversal, and it uses time complexity of approximately O of n and the space complexity of O of 1. So it's better than the recursive and the iterative, because in the iterative approach also we use stacks, or we can use queue, and then in the recursive call we have the stack space, right? It uses O of n time complexity. But if I talk about this Morris traversal, we do not require any extra space, right? So what I have done is I have written the algorithm here. Okay, so this is the entire algorithm, this one. Okay, and I'll do is I'll dry run this algorithm on this example. Okay, this is a binary tree that I have made here. Then I'll explain you the intuition behind the algorithm, and then I'll show you the code. Okay, so let's start. So we know that this is the root node, right? This is our root node. So I put it here, okay, as root. Now what does the algorithm say? It says go to the left node. Okay, so I'll go to the left node, that is this. Now if the left node is a null pointer, is 2 a null pointer? No, it is not a null pointer. Yes, then what do we have to do? Go to the extreme right node. That means from here I'll go to the right, I'll go to the right, and then I'll go to the right and I'll find a null pointer. Now I cannot go any further. If you reach back the same root node, no, I reached a null pointer. I started from the left node and I went to the extreme right and I reached a null pointer. So if you reach a null pointer, what you will do? Thread was not created. This means thread was not created. Now what is this thread? As of now, don't worry about it. It is not a very complicated kind of thing. Just uh, just assume that thread is just a connection. Okay, it is a connection between two nodes. So if you reach a null pointer, yes, indeed we have reached a null pointer here. That simply means that thread was not created. So create one pointing to the root node. So that simply means that I will have to create a connection from here, and it should point back to the root node, and then go to the left node of the root node. Okay, so let's do it. What I'll do is I'll create a thread. Okay, now what is a thread? As I said, it is just a connection between the extreme right node and the root node. Okay, and this thread is the right pointer, not the left pointer. This is a very crucial point that you should remember, that a thread is always created by the right pointer and not the left pointer. Okay, now and then go to the left node of the root node. So that simply means that my root now becomes the left node. Okay, so let's do it. So what I'll do is I'll take my root here. Fine. Now again I'll just repeat the algorithm, right? So what does the algorithm say? Go to the left node. Okay, so what I'll do is I'll go to the left node. Okay, I went to the left node. It is not a null pointer, so go to the extreme right. So from the left I'll go to the extreme right. Again I found a null pointer. If you reach a null pointer, that simply means thread was not created. So create one pointing to the root node and then move to the left node of the root node. So I'll create a thread starting from the left to the root, and I'll move my root to the left, right? Very simple. Okay, now again we'll follow the algorithm. Go to the left node. I reached the left node and I found out that it is a null pointer. If the left node is a null pointer, print the root node value. Okay, I'll print the root node value, that is 3, and then go to the right. Now I'll go to the right. So left I found null pointer, I printed the root. Now I go to the right. So if you remember, we created a thread by using the right node, right? So from the right node we'll go to the 2. Okay, now we have come here. So now my root is here. Okay, my root is here. Just a second, this is my root. Okay, now again go to the left. Okay, I'll go to the left. Now, if left is not a null pointer, go to the extreme right. I went to the extreme right and I reached back 2. Now, see this line, this particular line. If you reach back the same root node, that simply means thread already exists. If it exists, break it. Print the root node value and then move to the right of the root node. Now, see, it's a bit important point. We started from this root node, we went to the left, and from the left we went to the extreme right. And when we started traveling from the extreme right, we again reached back the same root node. If at any point this thing happens, that is, you start from the root node, you go to the left, and then from the left you go to the extreme right, and you reach back the same node, that simply means that thread is already existing. That simply means that you have already created a thread. In such a situation, you will have to break this thread. Why break this thread? Because originally this connection was not there. This right pointer of 3 was pointing to a null pointer, right? That simply means that the traversal of this left subtree is already done. So you will have to break this thread. Once I'll just end this algorithm and explain you the intuition, you will get everything. As of now, just remember it. We will have to break the thread. So what I will do is, I'll break the thread. And now it points back to null pointer once again. Okay, I'll not show it here. Okay, so now what we have done is, we have broken the thread and I'll print the root node. So I'll print the root node as 2. So I'll print it. And then what you have to do, and move to the right node of the root node, that is, I come here. So now my root is 8. My root is 8. Fine. Let's follow the algorithm once again. What you have to do, you have to go to the left node. I went to the left node, and then you have to go to the extreme right. Okay, it is a null pointer. If you reach a null pointer, that simply means thread was not created. So create a thread pointing to the root node, right? Create a thread pointing to the root node and then go to the left node of the root node. So now I'll move to the left of the root node, that is, this is my root. So I'll move to the left, that is, I'll come here, right? And I'll have to just write it once again. So now my root is this, right? Now my root is 4. Fine. Again I'll follow the algorithm. You go to the left. Now here I reach a null pointer. So you went to the left and you found out that the left is a null pointer. If this is the case, print the root node value and then go to the right. So I'll simply print the root node value, that is 4, and I'll go to the right, that is, I'll come here, right? So now my root is 2. Now my root is 2. Sorry, 1. I'm sorry, not 2, it's 1. Fine. Now go to the left node. I went to the left node. It is not a null pointer, so go to the extreme right. Now once I reached right, I found out that it is a null pointer. If you reach a null pointer, thread was not created. So create a thread pointing to the root node. Okay. Then what does it say? And then go to the left node of the root node. So this is my root node. I'll go to this left. So now my root reaches here. Fine. Yes. Now again I'll follow the algorithm. What is it saying? Go to the left. So I went to the left. It is a null pointer. If it is a null pointer, what do we have to do? We have to print the root node and then go to the right. So I'll print the root node, that is 6. And now when I go to the right, I'll reach back the root. So once again my root becomes 1. So now my root becomes 1. Okay, fine. Now again go to the left. I went to the left. It is not a null pointer, so go to the extreme right. I went to the extreme right and I reached back the same node. If you reach back the same node, what does it mean? It means that the thread is already created, right? Once again I'll repeat. I started from 1, I went to the left, and then from there I went to the extreme right and I reached back 1. So that simply means that thread is already existing. So I'll have to break the thread. Breaking the thread again simply means that pointing it back to the null pointer. Okay. Once you have broken the thread, you print the root node, that is, you print 1. So I'll print 1. Okay. And then you move to the right of the root node. So right of the root node, again, right of the root node is this, right? So now my root becomes 8. So I'll just write here my root now becomes 8, right? This is my root. Fine. Now again I'll follow the algorithm. From the root node go to the left, and from the left go to the extreme right, and when I went to the extreme right I again reached back the same node. That simply means thread is already existing. So break the thread, that is pointed back to the null pointer, print the root node, that is 8, and then after that what do we have to do? Move to the right of the root node. So now I'll move to 2, right? So now I'll move to 2. So now my root becomes 2. So this is my root. Fine. Yes. Now what do we have to do? We have to go to the left node. So I went to the left node. I found out that it is a null pointer. If it is a null pointer, print the root node, that is 2, and then go to the right. So now I'll go back to the right, that is this. So now my root is 1. Now my root is 1, right? Okay, so now my root is 1. Now again, excuse me, we'll go to the left node, go to the left node, and then we'll go to the extreme right, and when we go to the extreme right we again reach back the root node. That simply means that the thread is already existing. So break the thread, that is pointed back to the null pointer, and then what do we have to do? We have to print the root node. So I'll print the root node as 1, and I'll just move this here. Okay. And after that what do we have to do? We have to move to the right of the root node, that is my root becomes 3. Now my root is 3. So now my root is 3. Fine. Okay. Now go to the left, it is a null pointer, so print the root node simply. So it will be 3, and now I move to the right. So now I move to the right. So this is my right. Fine. Again same process, move to the left. I found out it is not a null pointer, so go to the extreme right. It is a null pointer. If it is a null pointer, that simply means thread was not created. So create a thread pointing back to the root node. Fine. And then after that what do? We move to the left. So now my root moves to the left. Just a second. Yeah. So now my root comes to the left. Now again same process, move to the left, right? Yeah. Move to the left. It is a null pointer. If it is a null pointer, you simply print the node, the root node, right? And then you move to the right. So I move to the right, and now my root becomes 9. Once again it becomes 9. Now again, once it becomes 9, you go to the left, you go to the extreme right, right? You go to the left, you go to the extreme right, and if you reach back the same node, that simply means that thread is already created. So you just break the thread, point it back to the null pointer, and then where do you move? You move to the you move to the right of the root node. And when you move the root to the right and you find out that it is a null pointer, that is the point where you will break it. Also I just forgot to print the root node, right? So I'll print the root node because this is the algorithm it is saying, right? Thread already exists, so break it and print the root node. So I'll print the root node, that is 9, and from here what I'll do is I'll go to the right of the root node, and once I find out that the right of the root node is a null pointer, I'll break the algorithm and I'll say that this is my in-order tree traversal of this binary tree by using this Morris in-order traversal. Okay. Now I'll explain the intuition behind this algorithm, like what is this algorithm actually doing, why are we creating threads, why are we breaking it, all these things I'm going to discuss. Okay. So one thing that we all know is in order traversal, what we do is we do the traversal of the left subtree, then we print the root node, and then we do the tree traversal of the right subtree, and then the subtree again becomes a new case, and then we again do this left root right? So if I talk about this tree, this is the root node and this is the left subtree and this is the right subtree, right? Now tell me, once you have done the traversal of this left subtree, then only after that you can come back to this root node, right? So this Morris in order traversal makes sure that you are able to reach back to the root node immediately after you complete the tree traversal of the left subtree. Now I know that this is the left subtree, and what will be the traversal if I do the in-order traversal? It will be like left, root, left, then you go left and then root, then you go to the right, then left, left, root, right, and then you go to the root once again, and then you go to the right, and then you go to the left and then root and right. Now the traversal of this left subtree is done. Now you, from this point, that is from the 2, from this point you have to go to the 1, because you know that the traversal of the left subtree is done. This is something that we are going to create by using this Morris traversal. We just want to create a thread from the last node of the left subtree, that will be the last node to be traversed in the left subtree. So if somehow we are able to create this thread, we will be able to reach back to the parent very soon. Like we'll just have to traverse to the right of the root node, to the right of the last node of the left subtree, and we'll reach the root node. So this is the intuition behind this algorithm. Okay, so what we basically want is, for each case, that is for each subtree, we just want to reach to the parent node as soon as possible. Like as soon as the traversal is done, we just reach the parent. This is what this algorithm is doing. So we make use of a right pointer, because we know that for any node we have two pointers, right? This is the left pointer and this is the right pointer. So we say that we will use the right pointer of the last node that will be traversed in that subtree, and we will point that right pointer to the root node, so that we reach the parent as soon as the traversal of the left subtree is done. Now why do we we have understood why do we create a thread, right? Now why do we break the thread? This is because just to restore the original tree structure. Because we know that 2 here is pointing to a null pointer. We do not want it to forever point it to the first, because this is a wrong the wrong structure of the tree. We have changed the structure. So what we do is, we start from the root node. We go to the extreme right, that will be the last node to be traversed in that subtree, and then we create a thread to the same root node. And once again, if we reach the root node, we check that if there is a thread. If there is a thread, just break it. That is the simple logic or the intuition behind this algorithm. And I'll just suggest you to do 2 or 3 dry runs on few examples, and you will be very clear with this algorithm. Right, now this is the code for this algorithm, and it's very simple. Like whatever I have written here, it's just coded it. I've just coded it in C++. So I can just show you the code. So what I've done is, so this is the function. So it is taking the root node, and then what I'm doing is I'm creating a mover pointer, okay, which is starting from the root node. So whatever I was writing here as a root will be considered as a mover, or it is just a mover pointer that I will be using in the code. Okay, so I said that there is a mover pointer and it is equals to the root node, and then the stop condition is while the mover is not equals to the null pointer. Now this case, if movers left is a null pointer, it is this case. Okay, so it's like, see, it's like we move to the left, we go to the left, and if it is a null pointer and if it is not a null pointer, these two cases are this. If it is a null pointer, this is this case, and if it is not a null pointer, this is this case, the else case. Okay, now if it is a null pointer, what do I say? Just print the root node, that is just put it into the vector and you move to the right. The mover moves to the right. And then if it is not a null pointer, that is the else case. So in the else case also we have two cases, right? What do we have to do is, we basically have to see, I'll just show you this. What we do is, if the left is not a null pointer, we go to the extreme right, and then we go to the extreme right. Either we will reach a null pointer or we will reach the root node once again. Okay, so see, I'll just tell you this. if you reach back the same root node, or you will reach a null pointer. So there are only two cases that may arise when you go to the extreme right node. Either you will reach to the null pointer, or you will reach to the root node. So here the root node is basically start. Okay, the start pointer basically means the root node, like the one I showed, the one I showed in the dry run. That root is basically start here. Okay, so what do I say? I say that you go to the extreme right, and if it is a null pointer, or if it is a start, like whatever comes first. If it is a null pointer, break it. Otherwise, if it is a start, that is the root node, you just break it. Now I say that if it is a start, this is this case. That is, if you reach back the same root node, that is, you started from the start and you reached back a start. If this is the case, then that simply means that thread already exists. So break the thread. So this last node, this is just making sure that we are able to, keep a record of the mover. So I'll just explain you this. See, it's like mover is moving from here to here. So I'll maintain a last node value. This is L. Okay. So it will start from here, L, and then we'll move to the extreme right. So it will be like this. Then mover will move ahead and the L will be here. Then mover will move ahead. Suppose this is a null pointer. So mover is a null pointer. And last is this last node that I will have to point to the thread, or if it is already a thread, I'll break it. So that is what it is. The last node is basically keeping the record of the node that will be from where the thread will be starting, or if the thread is already starting from that node, we will break the node. That is what it is meaning, right? So yeah, so this is it. This is just simple, keeping a record of the last node so that we can point it to the null pointer. That is, we can create a thread from it or break the thread from it if it is already existing. So last node is equals to right. This is basically this breaking the root node. Okay, sorry, breaking the thread. And then you print the node's value. This is it, print the root node's value, and then you move to the right. So you move to the right. This is it. And now this case is this one. If the thread is not there, so you create a thread pointing to the start. The start is again simply the root node, right? So if the thread is not there, what you do is you create the thread, right? And then you move to the left. So you move to the left. This is it, right? So this is the simple code of this. And if you just compare this logic, like if I show you, if you compare this algorithm, this logic with this code, it is just the translation of this logic, the logic in English into C++ code. It's very simple and it's very intuitive as well, right? So I hope you have understood this algorithm. And if I talk about the time complexity, is nearly it's O of n, and if I talk about the space complexity, it is O of 1, because we are not using any extra space, just this vector to return the in-order traversal, right? And also one more important point, I can just show you the pre-order traversal as well for this. Okay, I have it written in my, yeah, this is it. So if I talk about pre-order traversal, you just have to make few changes. Like here it was in-order traversal, you change it to pre-order traversal. Okay, you take the mover's value from this if, and in the else only in this, that is if it is equals to start, sorry, not this one, you will take the you will input into the vector the value in this else statement. Why don't you do it here, or why don't you do it here? This is simply because we do not want the nodes to be repetitive. That is, we might reach to the same node more times in this else block. That is why we want just the root node to be entered only when it is it is only when it is reaching or we are reaching that node for the first time, because that is what pre-order traversal is, right? That is, we print the root, we go to the left and right. The first thing that we do is print the root. So that is why we are putting this here, the in place back thing, we are putting it here. And if you have not understood it well, just one thing I'll tell you, just take a copy and take a pen and just do dry runs on a particular tree, and you'll understand it very well. So yeah, so that was from my side, and I hope you have understood it very well. And see you guys in the next video then. Okay, bye.